So good afternoon, everybody. First of all, I'd like to thank the organizers for giving me this opportunity to be here at this meet. So I'm Raka from University of Kolkata, and the work I'm going to describe is this is part of an ongoing work that I am doing with my PhD student Ovinabo Mukherjee, and I'd like to acknowledge some useful discussions I had with Professor J.K. Bhattacharjee and Dr. Arjo Dhar. So first of all, about fermionic superfluidity. So we know that just like their bosonic counterparts, fermions also can show superfluidity, like in helium-3. So whenever two fermions can pair up to give rise to something like a boson, then we can have superfluidity, just like two electrons can pair up and give superconductivity, and in helium-3, two fermions can give rise to superfluidity. So similarly, for charge neutral atoms also, two fermions can combine via magnetic Fishbach resonance or optical Fishbach resonance, where we can have fermionic superfluidity. Just a second. Sorry. So this is just a picture of the experimental achievement of fermionic condensates back in 2005 by the group of Marcus Greiner and Deborah Jean. So the keys, I'll just tell a little bit about the backstory and then about our work. So this is about the fermionic pairing. So the pairing can take place in between two completely different fermionic species, like sodium and rubidium or sodium and lithium, or it can take place between two hyperfine states of the same atom, just analogous to Cooper pairs. So the question or the problem that has been widely investigated also is what happens when there is a population imbalance in the system. That is, you have one species more in numbers so that you cannot pair all of them up just like the Cooper pair way. So the question people wanted to address is what kind of novel phases can emerge out of this imbalanced pairing. So here I'd like to quote an analogy from one of the talks by Wolfgang Ketterle, who first achieved one of the first achievers of BEC. So he just described it like this. Suppose you have a dance floor where you want to have dances going on in pairs, and now one of the species have more numbers than the other. So what kind of solution can you provide so that the dance can sustain? So one of the solution was that, okay, you expel some of the people from the dance floor and let the rest continue with their dance. And another solution was like this, okay, why not devise a new form of dance so that everybody can participate? So if we come to this analogy, so this is a phase-separated state where the excess unpaired fermions, these are expelled from the system, so they form a free Fermi liquid and the rest form a superfluid. And then there can be this new form of dance kind of thing. So you have a homogeneous system in real space, but if you probe enough into the momentum space, you'd see that there is a free Fermi liquid kind of structure between two breaching momentums, and in the rest of the momenta in the momentum space, it is superfluid Cooper pair-like pairing. And another possibility is one novel kind of dance that they call FFLO, named after Fulde, Ferrel, Larkin, and Ovchinnikov. So it is a finite momentum pairing. So unless the Cooper pairs with a zero momentum pairing, we now have some k plus q and bonding with a minus k plus q. So the resultant combination has a finite momentum. So when via magnetic or optical Fishbach resonance, these fermions are allowed to form a bosonic molecule, you don't have zero momentum bosons, but a finite momentum bosons. So starting from here, the question we wanted to address is what kind of, okay, first of all, I'd like to say I'm a theorist, but this field is closely related to experiments. And experimentally, although theorists have suggested this kind of novel phases, these are notoriously difficult to detect experimentally. So people often try to suggest indirect ways so that these phases can be captured or their dynamics can be studied. So here we consider a collection of fermions in optical lattice. So you just have counterpropagating laser beams forming a periodic lattice, and fermions can be trapped there. And we map that in a Hubbard model. Again, that's the common practice to describe fermions in an optical lattice. So we just have the standard Hubbard hopping and also the on-site interaction term U. So now as of their dynamics, this is my Hamiltonian. So what we have here, in addition to usual terms that emerge in Hubbard models, we have this Fishbach resonance term that allows two fermions to connect and form a boson, or one boson to split up and form two fermions. And now the dynamics can be described in terms of So about those novel phase structures, we focus on three particular structures that I just briefly described. I am just drawing them in analogous to one-dimensional Hubbard model. So when you have phase separation, you have like this, that you have paired fermions staying here and the rest unpaired fermions here. In breached pair kind of structure, where there are two breaching momentas from K0 to Kf and minus K0 to minus Kf here, two cuts here. And there is this FFLO where there is the pairing takes place for K minus Q to K plus Q by 2 kind of K minus Q by 2 to K plus Q by 2 kind of structure. So we consider these structures and we study the dynamical equations. So what emerges out of these equations is this, that suppose I consider the natural fluctuations of the system. So we basically do a mean field and then add fluctuations on top of that. So if I study the dynamical equations, what we find is that only though the condensate fraction will show some periodic fluctuations, and that omega values corresponding to those fluctuations can be extracted from these dynamical equations. So this, I forgot to mention one thing, that here this epsilon b is one crucial adjustable parameter in the system, that by applying an external magnetic field in the Fishbach scenario, we can adjust this epsilon b, the threshold energy for formation of bosons. So this is how these omegas vary as my detuning or this threshold value is being changed by applying a magnetic field. This is for a population balance structure where everybody can pair up the BCS way. Now, if I consider the population imbalance cases, so these are the three structures, and we see that again, this omega versus epsilon b curves are almost similar. So here there is a region where we do not get any real solutions for omega. Imaginary solutions we neglect because they would either mean an exponential growth or a decay, so an unstable solution. Next, we have two frequencies. So if you consider the condensate fraction, that is b dagger b, you would get a difference between omega 1, omega 2 as your frequency, and also omega 1 and omega 2 independently. And then beyond a certain value of this detuning, you continue to have only one single omega. This is for the breached pair. And for the two other cases, the region where we got two solutions is smaller in span. And for the rest, we have one single frequency. As we saw that here is a straight line behavior far away from the resonance. So we just try to fit it and extract the slope and the intercept from these values. And we wanted to, the previous pictures were for one specific amount of imbalance, that suppose my n up is majority in my system and n down, we just call up and down to continue our analogy with spins. In practice, they are completely different atoms. So if my n down by n up is 3 by 5, that value I have chosen and map for all these different structures. And then I want to vary my population imbalance in the system and want to see how these values of A and B, that is my slope and intercept, changes as my population imbalance is varied. So here are the pictures. So in x-axis, this is a population imbalance. So p equal to 1 means only one species is present there, the other is completely absent. And p equal to 0 means there is no population imbalance at all. So as you keep changing the population imbalance, this is how your A's and B's, this is for A, and for positive detuning, that is my magnetic field H is greater than H naught, the resonance value. This is for the B, the intercept for, again, for a varying population imbalance. This is for negative detuning, that is on other side of epsilon b when my magnetic field is lesser than my resonant magnetic field value. And this is how my A changes with the population, and this is how my B changes with population. So these are all show smooth and monotonic behaviors, except here you get my A increases with an increasing population and my B decreases with an increasing population. So these are all. So to put it in a nutshell, what we saw is that, okay, so although you cannot, you may not be able to detect those exotic pairing structures experimentally, you can have an indirect signature if you just record how the fluctuations change with your magnetic field or whatever external parameters the system is subjected to. And that allows you to detect whether you have a phase separated system or a bridge pair kind of system. That's one thing. And also you can have a record of how much population imbalance was there in the system, because your omegas carry a signature of that. So as you keep changing your P, the nature of the curves omega versus epsilon B also changes accordingly, and that can give information about what kind of system you had originally in your system. So that is all. I'd like to thank you for your kind attention.